H PQ. HPQ cohomology is trivial for all PQ except for all PQ with Q with positive Q. That's it. And now I have a question. Why should we take why this condition is important? So what happens with HP0? What is this guy?
Space of homomorphic forms.
Yes, and this is non-empty, right? Yes. It's a space of homomorphic p-forms. Non-trivial space. And H0, 0 are holomorphic functions. And we have started to prove. So what is done? Proved. So n is the dimension of m. It's n. Proved for n equal 1. Now n greater or equal to 2. We have proved partially that the Poincare lemma. We have done, it is reduced to the case of 0Q forms. And so we have shown that it is enough to prove for 0Q forms. And we have done induction by, so we have introduced the following subset of indices K, which is, so given a differential form, since it is O0Q, it takes the form sum of A G of X, the Z bar G, where G is G1, etc., GQ. That's it. And now, for the given form W, let us introduce the set of K. K of W is the union through all the non-zero coefficients, the corresponding indices, G1, etc., GQ. So we take unions of these subsets for all these terms. And we proved our Poincare lemma by induction in the cardinality of the set K. Induction base. So we know that the cardinality is greater or equal to Q. Induction base, the cardinality is exactly Q. And this was already proved. And now we have to prove induction step. So we have let the Poincare lemma be proved. So what is our goal? Goal, given omega in the space equation of the type 0Q, which lies in the kernel of differential, show that omega is the differential of something. That's our goal. And this was what we have done for the induction base. And for the induction step, we have to do the following. Induction step. So that's we have to prove. Let us assume that we have proved the induction, the statement. For the cardinality being equal to L, so let us prove for cardinality being equal to L plus 1. So let us note the following. The cardinality, the interesting cardinality is a cardinality which is less than or equal to n. Because if the cardinality is bigger than n, there is nothing to prove because the form is identically 0. Because we wedge multiply some coinciding dz bar. And so we have to prove. So now let us let us consider that 1 lies in K. We can reorder our coordinates to achieve this inclusion. Just this equation of choose of order of coordinates. And we let us split our form into two parts. So we know that d bar of omega is equal to 0, and we write down omega is sum of g I of x dz1 bar dzi bar plus this is the part containing z1 plus the sum of aj with one not line in j, aj of x dz j bar. That's it. And we know we have this condition that the d bar differential vanishes. And this implies the following restrictions, the following constraints on gy. So d bar omega vanishes. The g I of x are holomorphic in zg for every g line which does not belong to K. Why it's so? Let's check this. Let us check that yes. So suppose that it is not holomorphic in some zj. Then taking the differential of the ji makes so after taking the d bar differential, we get a new term, which is this wedge dz bar. So it is dz1 bar, dz bar, and everything else. And no similar term will appear here after taking the differential, the d bar differential here. Because here there is no z1. And in order to cancel this term out with this, we have to make appear here the zg bar. But the zg bar, if the zg bar appears, then the z1 will never appear. So there will be no cancellation. If this is not holomorphic in some zj with j not in k, then there will be no cancellation between this term, this extra zj term, and this. And therefore, there is no chance to get the zero differential. So that's it, holomorphic. Now, what holomorphicity allows us to do? Let us take the expression, the gi of x times the z1 bar. I claim that there exists a function f I holomorphic in the G for every G, okay, such that the f, the bar f, the z1 bar is equal, the fi is equal to the gi. This is the result of the case of one variables. We have seen that this equation is always solvable in one variable. And if the function depends on extra parameters smoothly, then the function f can be chosen to depend smoothly on the extra parameters. And if g depends on some parameters holomorphically, then the function f can be chosen to depend holomorphically on the same parameters. And so that's the result of the case of one variable. And let us use this result in order to simplify our form, in order to perform the induction step. So now let us do the following. Let us take alpha I to be the form f I dz I bar, and let us take with omega tilde to be omega minus the sum of lambda I of minus sum of alpha I. That's it. And let us take minus d bar of this. Sorry. So what we have done, we have modified our form by subtracting a coboundary. And what we get? When we take the d bar differential of alpha, we cancel these terms. First of all, we cancel these terms. And we get the sum of b g of x dz b s of x dz s bar, and with one not lying in s, and s lies in k. So k without 1. Because of the following. When we differentiate this form, there will be no d bar differentiate. There will be no zj outside k which will appear. So what we get here will be strictly inside k, and the one part will cancel out. And what remains is everything else except for 1. And therefore, we get that k of omega tilde, the index set of the new form omega tilde, lies in k of omega without 1. And its cardinality, so let us know this k tilde. The cardinality of k tilde will be strictly less than the cardinality of k. And therefore, the form omega satisfies assumptions of the induction hypothesis, because it's bar differential vanishes because the bar squared is equal to 0. And k tilde is less than or equal to a. And therefore, omega tilde is a differential of something. That's it. And therefore, omega is a differential of h plus sum of alpha I. And we can denote this by h. And that's it. This finishes the proof. This finishes the proof of the Poincare lemma in full generality. So let me stop here for a while. Maybe you will have some questions. Okay? Okay. Okay, so now let me next state the following important generalization of this statement. Theorem. Theorem. So let M be a Stein manifold. For those who see this for the first time, I would say that it's equivalent to the statement that the property being submanifold in some Cn. Then the lemma, the statement of lemma of the Poincare lemma holds that h pq of M vanishes for every positive q. But I will not prove this theorem right now because it is more tricky than this. But I would prefer to say some words and to explain some reason for that. Why this property is useful? This property is useful because it allows to prove that some locally defined object on a complex manifold is a globally defined object. Let me provide some basic example. Definition. Let A be an analytic subset A is called a hypersurface if each neighborhood, each point of A has a neighborhood in the ambient manifold where there exists just one function whose zero locus is exactly the intersection of A with U. So hypersurfaces are analytic subsets which are locally defined by just one function. Or just one function can be defined. So what I would like to state is the following theorem. For every hypersurface in the polydisk delta is there a locus of a function. There exists a holomorphic function whose zero locus coincides with A and F globally defines. Globally defines means that at each point f is the simplest possible function which vanishes at a. To be more formal, I would like to pass to some details in order to define formally what does it mean a function f locally defines a locally or globally. And I would like to say that the Poincare lemma, which we have proved right now, has a direct relation to this theorem. It allows to prove this theorem. So let me first prove the following proposition. A is hypersurface if and only if A is of pure codimension 1. This means that each component of its irregular part has codimension 1. This is if and only if. So let me prove it. That's it. So first let me prove this direction. Let us prove that if A is locally defined by one function, then it is of pure codimension 1. Actually, the proof is like this. Zora locus. So without loss of generality, we can consider that f is the Weierstrass polynomial. Then A is local covering. So in a Weierstrass polydisk, A intersected with U without preimage of some analytic subset is a covering over the disk of dimension n-1 without analytic subset. It is a local theory of hypersurfaces which we have seen. So we have seen the following. How to factorize a Weierstrass polynomial into irreducible factors. We have seen, we have done this in two ways. First way was algebraic way with Gauss lemma, and the second way was analytic way, geometric way. We have proved that if we take Weierstrass polynomial restricted into Weierstrass polydisk and take it zero locus. And let us project its zero locus to the base of codimension 1. And we have found in the base an analytic subset such that if we cross it out, then on its complement, the zero locus is a covering, topological covering. And it has topological covering, and over the complement to the analytic subset, it is regular. It is regular, and we know that it clearly the regular the covering is of codimension 1, is a local submanifold of codimension 1, and therefore the analytic subset equation is a closure of this regular of this part of regular part of the covering part, and therefore it is of pure codimension 1. And the other way is a little bit more, it's basically the same, but maybe it's a bit more tricky. So let us prove this. So we know that so let's assume that A is of pure codimension 1. Let us prove that A is hypersurface. So A A is locally, so locally, the intersection of A with some small neighborhood is a zero locus, f1, etc., fk is equal to 0. For example, A lies in the zero locus of the function f1, right? And if we choose an appropriate coordinates, we assume that f is Weierstrass polynomial. And we do the same theory for the zero locus of f1. A denoted by z. And let us do the same for z. So we know that z minus the complement of p minus 1 of b. B is an analytic subset downstairs. And this we know that it is covering. And this covering contains a part of A. So A lies here. And this covering is a union of a finite union of regular connected components, right? And we know that A lies in this the complement of A to pi minus 1 of B lies in this covering. And we know that this is of codimension 1. And this is of codimension 1. And for some rather obvious reasons, which I will not, on which I will not stay too much, I would say that this part of A is a union of connected component of this guy. Because of the following. Let us intersect A with a connected component of this. The intersection will be either a small analytic subset or the whole component. If it is a whole component, we are fine, but it cannot be anything else. It cannot be a smaller subset, because if the intersection of A with a component is a small analytic subset, this means that this small analytic subset is a component of A. But it is not of codimension 1, it is of a bigger codimension. That's it. And therefore, finally, we get that A is a closure of union of connected components of this. But we know that union of connected components of this is zero locus of some Weierstrass polynomials, of some product of irreducible factors. And what we get? So let finally A locally means that we have intersect everything with Weierstrass polydisk. What was it? Locally A, the complement of this, is a union of connected components of some connected components of Z. Each connected component corresponds to a irreducible factor of f1, of the function which vanishes. Irreducible factor g with the index g. And then A can be written as zero locus of g of product of these irreducible factors. Yes, that's it. We just take A. We take A is union of connected components. For each connected component, we take the corresponding irreducible factor which defines this component, and we take this. It's the product of the irreducible factors which correspond to components of A. And that's the function which defines A. It vanishes exactly on A locally. And this basically follows from construction, that it vanishes exactly on A, because A is a union of closure, A is the closure of union of components, and this guy vanishes exactly on the closure of union of components. Yes. And what we get finally? let us denote this product. So let us denote this product by G sub A. So I claim that G sub A generates the ideal in the local ring of functions vanishing of germs of functions vanishing on A. This means the following: we took a point, we're working a point, base point, and we consider the ideal of functions which vanish, whose restriction to a small neighborhood vanish on the intersection of this neighborhood with A. This is the local ring of functions vanishing on A. And this ring appears to be ring of principal ideals. So this ideal of functions vanishing on A is principal. It has generator. And this is the generator we have just constructed. And we have this generator has another bonus. The bonus is the following. It vanishes exactly on A locally, but simultaneously its differential is non-zero on open-ended subset locally in A. And this defines generator uniquely. So generator is unique germ of functions which vanishes on our germ exactly on our germ subset, and which has this additional property that its differential is non-zero on an open-ended subset. This is a criterion. And this open-ended subset is just the complement of A to the branching locus. Because non-vanishing of differential means exactly that the roots of H trust polynomials are simple. Now we are ready to state what is globally defines A. So now definition. F let F be a holomorphic function. Let A be let A be analytic subset. We say that F defines A globally if A is exactly the zero locus of F, and second, for every point x at A, the germ of F at x generates the ideal let us denote this ideal by I sub A. If the x is a base point, we are working. The ideal I x. The ideal of germs of functions vanishing on the germ of subset A at x. And now we have finished to formulate the statement of the theorem. The theorem is already formulated. For every hypersurface, for every subset which is an analytic subset of pure dimension 1 in the polydisk, there exists a function whose zero locus is exactly A, and whose germ at each point of A generates the corresponding ideal. And yes, that's it. This holds in a polydisk, and this holds on every contractible Stein manifold. This was actually because to get this statement, we need not only definition of Dolbeck homology, but we have also some topology. We need also. Now I have some time, and I would like to make some introduction how to prove such kind of results. And there are some other similar results stating that given a hypersurface in a polydisk, a holomorphic function on the hypersurface, there is a statement that states that this function extends to the unbound manifold, the unbound polydisk. Now, how to prove this? Let us pass to Cousin problems. So, Cousin problems. So, given complex manifold, M, and covering U calligraphic, covering by open subset. And we have, let us consider a group. So I would prefer not to deal with shift theory, but I would like to general shift theory. I would prefer to concentrate myself on some holomorphic stuff. So let us consider definition. One concycle. One concycle is a collection of functions f alpha beta defined on the intersections, which satisfies the following relation: f alpha beta is equal to minus f beta alpha as antisymmetry, and cocycle relation f alpha beta plus f beta gamma plus f gamma alpha is equal to 0 on the triple intersections. Yes, that's it. It's one cocycle. Functions can be of different class: holomorphic, non-holomorphic, etc. These can be also not functions, but elements of some groups. Now, coboundary. One coboundary. So let us consider f alpha, some functions on our covering domains, and f alpha beta, set f alpha beta to be f beta minus f alpha, which is clearly defined on intersection. And this is clearly a cocycle. So one coboundary is always one cocycle. And additive Cousin problem. Given one cocycle and this is, by the way, this collection is called zero cochain cocycle F alpha beta. Find zero cochain F alpha such that F alpha beta, F alpha satisfying this relation, whose co-boundary is our cocycle. It is additive and multiplicative. With the same, but with multiplication. So multiplicative. F alpha beta is equal to F beta alpha minus 1, and F alpha beta, F beta gamma, F gamma alpha is equal to 1, etc., etc. Everything where plus is exchanged into product. And the same, and multiplicative Cousin problem. The same. So the problem is the same, but just for multiplication, not for addition. And now, what about this what about relation between Cousin problems and this theorem on hypersurface? The relation is the following. Theorem. Let on complex manifold every multiplicative holomorphic Cousin problem is solvable. Then this theorem, theorem 1 holds on this manifold. This means that on this manifold, every hypersurface is zero locus. It can be globally defined by some holomorphic function. So how to prove this theorem? Proof is not difficult at all. So given hypersurface A and M, how we construct holomorphic multiplicative cocycle. One cocycle. How to do this? So we take the following functions. So G, we take the covering. So covering of M, U1, just also use U0, so is one open set, is M without A. And we take the function G0 identically equal to 1 on U0. And let us take, so this is one element of covering. And let us take locally finite covering of A. So given a point X in A, let us consider a neighborhood such that A intersected with U is a zero locus Ux of some function. And fx is defines this intersection. This means that we assume that fx generates the ideal of the set A at x. Then this immediately implies that it generates the corresponding ideals at each close points, because we know that the set, if we take in small neighborhood U small enough, we can achieve that this from the restriction of this function to this neighborhood, to the intersection of A is this neighborhood, has differential at the point of A, which vanishes, which does not vanish on an open-dense subset in this intersection. And this property is independent on the point x. Property of a function being having differential that it doesn't vanish on an open dense subset in this intersection is independent of this point. And since it is true, then it generates ideal at each point in the same intersection. So f defines A here. And the defining function of A is unique up to multiplication by unity in the local ring. Up to multiplication by function, by homomorphic function, which doesn't vanish. And now let us take intersection of two neighborhoods. Ux intersected with y. Here we have fyx, and here we have fy. And here we know that on this intersection, here fx, here fx divided by fy is holomorphic. Holomorphic which doesn't vanish. This quotient is holomorphic. Because we know that at each point this function generates the same ring, they are generators of the same ideal, and therefore their ratio is something holomorphic non-zero. And what is this? Let us call this guy fxy. Fyx. And this is one cocycle. Multiplicative one cocycle. Sorry, I would like to say that I would like to change notation. I would like to replace all the f by g, in order to avoid confusions. Sorry for that. But this guy I will call f. And this is one cocycle. And it is not a coboundary in the obvious way, because this is a kind of coboundary, but these functions are not non-zero. They do vanish. But the solution of multiplicative cousin problem is in the collection of non-vanishing functions. Because multiplicative, this means that we deal with multiplicative group. And therefore we have to forbid any vanishing. So one cocycle. And suppose that, let fyx be coboundary. Coboundary, this means that fyx is equal to sum fx divided by fy, where fx, fy doesn't vanish at all. Then what do we get? What do we get? We can collect. Let us get this, and let us do the following. Let us multiply. Let us denote by f, just f without anything, gx divided by fx in x. And let us write down the same expression.
Fx
let us suppose that f is coboundary. Suppose that the cousin problem can be solved. It's coboundary. This is therefore on the intersections. This can be represented as a ratio of non-vanishing holomorphic functions. Non-vanishing holomorphic functions. And let us consider the following auxiliary function. Let us divide each gx, which vanished somewhere, by fx. This is here, and this is. And let us compare these two guys on the intersection. I claim that we have equality. Because of the following. Let us take their ratio. When we take their ratio, then everything cancels out. By definition. And therefore, f is globally defines A. It perfectly generates all the ideal of A at each point, and it is a global holomorphic function. Because it is defined on small neighborhoods, but it is the same on the intersection. But one moment here. Here we have done this. Here yes, it's okay. It works. And that's about importance of to solve cousin problems. And now I would like to prove this following, sketch the proof the following theorem. That on so our goal is to solve multiplicative cousin problem. But the solution of additive holomorphic cousin problem is close to it. It is not the same. It is not the same, but it is close. The difference, a gap between solution of additive cousin problem and solution of multiplicative cousin problem, a gap is topology, is given by topology, by cohomology with integer coefficients in some degree. But I will not discuss, I will not have no time to discuss topology in more details. I would like to prove the following theorem. On polydisk, every additive holomorphic cousin problem is solvable. So step one. So problem is following. Step one is every C infinity additive cousin problem is solvable, and our goal is to concentrate ourselves on step two. Step two, C infinity versus holomorphic. How C infinity solvability implies holomorphic? This is the main issue which I would like to discuss first of all, and if I have time, I will discuss step one as well. Step one is, roughly speaking, is done by partition of unity. So let us consider solution. So let f alpha beta be a holomorphic additive Banco cycle. Let G alpha be smooth solution of Cousin problem. This means that G beta minus G alpha is equal to F alpha beta on intersection. This is holomorphic, but this isn't. This are not. This are not. This is just smooth function. Now, let us do the following trick. Take d bar differential. D bar of G beta minus d bar of G alpha is equal to 0. Because d bar of holomorphic is 0. And therefore, the collection of forms, the form omega, which is given by d bar of V alpha on U alpha, is global d bar closed 0,1 form, right? It is locally d bar closed, so d bar is equal to 0. It is closed. And therefore, but the first cohomology is trivial of our polydisk. The first cohomology of our polydisk is trivial. What I'm talking about holds whenever, in general, wherever you have this definition of cohomology. And therefore, there exists a function h C infinity in polydisk, for which whose d bar is equal to omega. And now let us do the following. So let us consider f alpha, which are equal to G alpha minus H. We know that f beta minus f alpha is equal to our equicycle, just by construction. And we know that f alpha is holomorphic, because d bar of f alpha is equal to d bar G alpha minus d bar H, and is equal to 0, because d bar H is our form omega, and d bar G alpha is also our form omega. This cancels out. And therefore, f alpha are holomorphic. And these are holomorphic solution of additive holomorphic Cousin problem, constructed explicitly by solution of d bar problem for 0,1 forms. And we have some time left in order to explain step 1, the solution of C infinity additive Cousin problem. So problem for cocycle f alpha beta of smooth C-valued functions. So to this end, let us denote, let us fix rho alpha partition of unity for covering by subset O alpha. This means that the support of rho alpha lies in U alpha. And let us construct explicitly the solution of this problem as follows. F alpha we are looking for is defined like this. Is the sum through U through all the beta which intersect our U alpha of the following. We take rho beta times F beta alpha. So, what is this expression? However it is defined. So, first of all, we take F beta alpha. F beta alpha is defined on this intersection, right? And we multiply it by rho beta, by function we support here in U delta. It is rho delta, support in U delta, right? And I claim that this is a well-defined function on U alpha. So here is a picture. U alpha, U beta, and here is support rho delta, right? Here is support of rho delta. And on this set, everything is well defined, but we don't need any definition here, because here rho delta is equal to 0. Here rho delta is equal to 0, here rho delta is equal to 0. So we take the function we defined here, and we extend it everywhere else in U alpha just by 0. And this is smooth, because of that. So this is well defined on U alpha, and we claim that this is solution. And this is solution of the infinity Cousin problem. We can check it immediately. So F beta minus F alpha. What is this? Let us write down explicitly. First of all, we sum it up through all deltas whose intersection with both U alpha and U beta is non-empty. And we can write down this part of sum like this. Rho delta times F delta beta minus F delta alpha. Right? And this guy, by cocycle property, it is equal to F beta alpha. Right? And next, we have to take into account the other delta plus sum through those delta for which this intersection is non-empty, but this intersection with U beta is empty. And here we take into account only rho delta times F delta alpha, right? Because, yes, rho delta times delta alpha. And, but we take here my sign will be minus. And here, and then there will be similar part. And what is this? Look at this condition. The intersection of U delta with U beta is empty. And therefore, this implies that rho delta restricted to U beta is identically equal to 0. And therefore, its restriction to the intersection of U alpha with U delta with u beta is also identically equal to 0. And to this intersection it contributes nothing. And for the same reason, the other part, the other sum will contribute nothing to the intersection. The other sum will be with f beta. And therefore, the only part which contributes something is this part. And this is being a partition of unity. This sum is equal to 1. And this is our cocycle. And therefore, this is a solution of our smooth problem. So that's all I wanted to talk about. I'm sorry for being not having time to tell the other part of program which concerned more advanced cohomology theory. But I have told that we have to finish everything next week, so including exam. So thank you very much for attention. So if you have some questions.
Да, у меня есть вопрос.
Да, пожалуйста.
Вот условие того, что все задачи Кузена имеют решение, оно как будто выглядит сильнее, чем то, что просто первая когомология по Чеху обращается в ноль.
Оно сильнее выглядит, да, оно сильнее, потому что Чех мы его делаем для стягиваемых областей. И более точно, когда мы изучаем когомологию по Чеху, то там мы строим ациклическое покрытие для данной группы, для данного пучка групп. Вот. Есть такое понятие. Так что вот локальные когомологии, они нулевые. Вот.
То есть могут быть случаи, когда когомология Чеха первая обращается в ноль, а какие-то задачи Кузена не имеют решения.
Я думаю, что такие примеры можно построить, иначе бы не существовало бы теории когомологии Чеха в таком виде, как она сейчас есть. Я так это не продумывал тщательно, как строить такие примеры. Но я думаю, что их можно построить при желании. Во всяком случае, это уж точно нужно. Вот ацикличное покрытие нам точно нужно, чтобы перейти от решения аддитивной проблемы Кузена к решению мультипликативной. Потому что делает аддитивная проблема Кузена? То есть мы можем из мультипликативной проблемы Кузена построить по мультипликативному коциклу, мы можем построить, так сказать, аддитивный коцикл. Но он не будет аддитивным коциклом, потому что там будет соотношение коцикла будет выполнено с точностью до целочисленной добавки. Но когда мы перейдем к старшим когомологиям, мы из этого можем изготовить целочисленный коцикл, уже два коцикла целочисленный. Вот если он, родимый, зануляется, то все хорошо, мы можем все подправить, и мы можем по мультипликативной проблеме Кузена построить управляющую ей аддитивную проблему. Если с целочисленными когомологиями второго порядка все хорошо. Нулевые. Вот. Потому что оказывается, что можно встроить ту же самую теорию когомологии, коциклы и так далее для целочисленных, для двух групп целых чисел. Просто построить целое число на пересечении и задать вопрос, можно ли построить целые числа на подмножествах, на покрывающих областях, так, чтобы были все отношения выполнены. Это целочисленная проблема Кузена, целочисленная когомология. Так вот, если вторые когомологии в этом смысле слова нулевые, то тогда из решения аддитивной проблемы Кузена мгновенно следует решение мультипликативной. И все, что касается гиперповерхности, следует. А вот оказывается, что эти целочисленные когомологии, которые я сейчас определил так грубо, так просто махая руками, они совпадают, вот чудо, с сингулярными когомологиями. Это теорема. А поскольку мы знаем, что наше пространство полидиск стягиваемый, то все когомологии такого типа, они нулевые. Но это некая наука. Там, в общем, как перейти от одних когомологий к другим, это некая наука.
Я лично знаю теорию пучков, я просто не видел так много настолько конкретно.
Да.
Скажем,
Конечно. Вот, да, Алексей, простите, пожалуйста, у вас то задание, которое вам присылал на семинар, оно у вас есть, вы к нему готовы, да? Вы представите. То самое, то задание, не состоявшегося семинара, вот оно на этот семинар. Вот, хорошо, спасибо. Так, ой, да, я должен дать приборы. Вот, я положу сюда.
Так, ну давайте что-нибудь посчитаем. Например, просто найдем d-бар дифференциал от некоторых дифференциальных форм. So we have holomorphic forms in two complex variables.
тут дубль в степени альфа или в квадрате?
В квадрате. В квадрате. Okay.
It's clearly zero because it's homomorphic platform. And the bar of homomorphic forms is zero.
Yeah, so yeah, here you don't really have to compute anything. Okay, so let me write down the rest.
Soll ich jetzt gut anfangen?
Mm-hmm.
So we can write in the whole book.
Mm-hmm.
And then essentially by learning so applied to
Mhm.
this product.
Yeah, so just differentiate the function. Uh-huh.
So you see. We can write this as
Mm-hmm.
well, and then we apply chain rule for d over dz bar to this expression. So I think it should be like that.
Mm-hmm. Mhm. Well,
And we can do d with a similar trick. So we can use the following relation.
mm-hmm. Yeah.
Well, and then the problem reduces to the similar computation.
Yeah.
So we get that's not inequality, but I want to set d bar of
Yeah.
this expression. This is and this is equal to
Yeah. Uh-huh. Okay.
Okay, just don't quite understand.
Which part?
Well, if we take this, I see. I had doubts about this function being smooth, but since the modulus is only non-smooth at 0, and this function inside doesn't take 0 values,
Yes.
it's smooth. Okay.
Uh-huh.
Yes. Of course, yes.
Okay. So let's proceed, and so let's consider differential forms on the unit disk. And let's find their primitives. Forms on so the first one is just the form dz with bar over.
Что это значит? Даже с чертой нам всем, как это понимать?
So the difference between just dz bar and dz with bar over it. So we take so we first take so how to say that?
Somehow I think that complex conjugation commutes with taking derivatives, so at least real linear derivatives. So it should be the same as like usual d of z bar.
Okay, so let's check if it's really the same. So how can we check that?
essentially what we try to understand is we can take a function, take the linear part of the point, and take conjugation, or we can take conjugation, then take linear part, and like then we get a commutative square out of it. But it seems clear, like if we say the Taylor series, we can apply term-wise conjugation. So it should make sense.
Yeah, so if it's just the R linear differential okay. Okay, and so what would be the primitive of this form?
Well, C bar, because we have D, like usual D is of Z bar is equal to D bar of C bar, because like the total differential of Z bar has no 1-0 part.
Okay.
So in case is also equal to 0 bar of C bar.
Okay. Okay, so F of Z DZ bar, where F of Z is holomorphic.
This is going to be f of z times z bar.
Sorry?
Well, it's going to be f of z times z bar. Because the d bar will not do anything to f and will just be applied to z bar. And as we established. Okay.
That's what you're saying. Okay. Okay. Yeah, so if you differentiate this, yeah. Okay, and let's consider now forms in two variables on a polydisk. We have Z1 bar minus Z2 bar.
find just one of limited because of course a lot of them.
Yeah, just one is enough.
So can I have an answer?
Mm-hmm.
Probably one of the simplest answers to write. I think we have to say that this is the bar or then we can apply this to linearity to C.
Mm-hmm. Yeah, so now let's consider let's consider the following domain, and let's consider a form. And let's find one of its primitives on this domain.
behavior I have.
Mm-hmm.
So, if we look at this expression, we could formally write however, this is not very good because logarithm of z bar is not defined as a single valued function in this domain, which is not simply connected. That is a problem.
Mm-hmm.
If we had a simply connected piece of this domain, we could find the corresponding branch of logarithm and extend it, and everything will be fine. But we can do the following trick. We can write this. Again, this is not a single valued function, but it's like monodromy is adding constant, so d bar and vanishes under d bar anyway, locally. It's all everywhere. So we have this, but this is and this is a real valued function.
Yes.
So we can how do I say? Well, it has like real analytic continuation in this domain. How do I say it?
Mm-hmm. Yeah. Mm-hmm. So, okay, and let's okay, so let's consider let's consider a counterexample to the d-bar Poincaré on a certain domain, which is going to be the Hartex figure. Yeah, so let us denote by omega I, zi minus 1/2. And let's consider one form. Omega, which is the following. let us check that this one form is d-bar closed. But omega is not exact.
somebody able to prove the first part, the bar is
Well, it's just computations and one has to look at like
So, Mikhail, I will represent the solution. Roger, would like to try?
Well, I don't know how to prove that it's not exact.
Just
the bar closed.
yes, just the easier.
Yeah, I can do it. First, we're gonna just apply the bar to the numerator. That gives us okay, yeah. Well, yeah, we gotta keep in mind that when we switch, there's going to be 2 here. So, okay, so I'm gonna write it as a choice. Make it a bit shorter. So, now, the denominator, this simple so is going to be 2 here. This one will stay. This is yeah. Well, so basically, let me just to multiply the 2 here, like W2 bars minus W2 bar times W1 well, so this this part of the form, there is no point multiplying it by this, it's just going to be 0, so we're left with only this, and this is going to be square, which denominator bar. Yeah, plus, so this one again, we only need to multiply to this one. This is going to be this, and well, there would have been a minus, but I'm going to need to switch. Yeah, so in the end, we have a sum of those squared modules of W1 and W2, and there is a power of 3. They will cancel out to the power of 2 again, and we're going to be left with basically from the first term it's going to be minus. Okay, I'll use the plus. Oh. Well. See, and here is going to be a minus 2.
So what is left after you have cancelled out this
No, I mean
the function in the numerator?
I messed up the signs somewhere because, well, there is a minus here, and then, well, what I should write by my calculations is this, but that's not correct because yeah, because if we're gonna switch, exchange the two, it's just gonna be 4 times the something where
Okay, let's see.
of course, like not here, but here. So yes. Like that, then like this, then it's that's it.
Yeah, so you just you need to take order into account when you multiply differential forms. Okay. So yeah, so we would like to show that there is no smooth function f on h such that omega is d bar of f. yeah, but at the same time, if we yeah, so if we if we allow singularities, then we may write omega is d bar of alpha, where alpha is well, it's not defined on all of H. And this is on okay, now, so let's suppose that we can find such a smooth function, and let's try to derive a contradiction. Yes. So suppose that omega is d bar of f. So what can we say? Also, let us look at the function f minus alpha. So what can we say about this function? So alpha is this.
Okay.
Yeah, so it's a primitive on.
It's a kind of primitive.
Yes, on a complement to.
Yes.
To this set.
Can you check this? It's really primitive. It's 1 over omega 1. Yes. It is 1 over omega. Above is 1 over omega 1.
No, it's. I think it's.
Omega 1 bar.
Yes, it's just W1 bar. Yes.
Okay. Yes, okay, when we take the bar of the numerator, we will get W1 bar, and then you divide by everything else, but when you take the bar of the denominator,
Yes.
then what you get is the bar 1 is So you indeed claim that it's in so can you maybe one has to check that it's indeed the case. Actually, it's a very nice idea. Yes, provide such a primitive. What we have to verify that everything is clear.
Well, also has an idea. Well, we have the decomposition of our domain polydisk, by its definition, and we could find a primitive on each polydisk, like one parallel, and compare them,
Okay.
and try to work from that. So,
Okay.
Okay, so but what you can say about this function? If you decide how is it different? So we have two primitives. Suppose we have two primitives. One is f, which is smooth,
Mm-hmm.
and the other one is alpha, which is like this.
Yeah.
What can you say about the difference?
well, when there was undefined, the difference is how.
Yes, the difference is hollow.
Yeah.
And now we have yes, the difference is hollow. And so we f should be equal to some holomorphic function plus alpha, right? And holomorphic means holomorphic from the definition domain. So holomorphic means yes, from here. Holomorphic from this component. And so the statement is the following: that we can correct the wild function alpha with singularities by some holomorphic function on this complement in order to get a infinity function, right?
Mm-hmm.
And the question is whether it's possible. But still, first of all, let us check that it's indeed primitive.
Yeah, so let's compute the bar of
this is still the calculation is beautiful, but it's well worth to do it ourselves.
Yeah. Okay, so maybe let me finish the idea, well, assuming for a moment this computation. If this function is holomorphic on the complement to the set, then then this function should be holomorphic on the entire H. So yeah, because well, because it is continuous, right, and holomorphic on the complement. So in particular, it is bounded locally in the neighborhood of this.
It would be locally bounded.
Because look at that.
Yeah, so we just multiply with this function to,
Okay.
yeah. And from here, so we should be able to derive a contradiction. So how? So H is a hard-text figure, right? Then G extends holomorphically to the bidisk. Yeah, and let's see what happens at the point at the point 1/2 in z coordinates, which is
So we know that the G holomorphic is holomorphic and there is this point at 1/2. So this means that it's holomorphic W1 and W2 is equal to 0, 0. And we have to get a contradiction of this from our construction. question, if it is holomorphic, then what would be its value at this point? The first question. And I think one can analyze what would be the value of G at our point. Because we know that F is smooth, right?
Mm-hmm.
And taking this into account, we can just calculate the value. If it is, well, we can find out whether this value is well defined or not. Which is this.
Yes, let's write. And what about the value of this function? Whether is it well defined?
No.
Why not? It's Glutsyuk is correct and not well defined. What is the problem with this function?
Well, we can, for example, choose two sequences of W in which the last part will either converge to 0 or to infinity.
Exactly, because we can randomly choose two sequences. For one sequence, the bar part of the expression bar fraction converge to 0, for the other part converge to infinity. While the first function is perfectly 0.
Yes.
And therefore it's not a function, it is not it doesn't have a well-defined limit.
Yeah, so we cannot extend it by continuity.
That's foolish, yes. It's true that the foolish about this problem is that our domain is not a polydisk, it's not a spine matrix, it's Hartog's figure.
Yes.
And for Hartog's figure, the debarkable theorem is false. And
Okay.
it's just false.
Okay, I think that's it for today.
Thank you very much. Thank you very much to everybody. And so in a couple of days I will distribute the exam information.
То, что вы присылали листки, я проверил. Ну, там все хорошо, мне кажется, и у вас, и у вас. Если я засчитал все, что мне присылали. Вроде бы.
Я хотел показать еще. Вот что я пытался сделать.
Ага.
Можно еще одно написать.
Алексей, формула ссылки правильная. 0,3 за экзамен, 0,7 за...
Да?
Правильно. Я еще проверил с Линой, там все правильно.
Хорошо.
Вот. Вот. Просто в силу антисимметрии можно написать такое.
Можно. Да, и теперь что?
Ну, то есть, что у нас есть.
Ага.
Как бы здесь живет альфа, здесь живет бета. И живет альфа минус бета. Это гомоморфная функция.
Да.
Вот, ну теперь скажем, что F, вот, то самое, которое мы предположили,
Да.
это альфа плюс F1.
Так, альфа на этот раз альфа у вас то же самое, которое там, или другое?
Да, то же самое, то же самое.
Альфа то же
Вот,
самое,
Альфа
да.
то же самое, но мы еще добавили антисимметричное к нему по переменному бета.
А, хорошо, да.
Мгм.
Вот.
Так.
F1 это что-то гомоморфное на U1, а F2 что-то гомоморфное на U2.
Мгм. Да.
Ну вот, тогда получается, что альфа минус бета плюс
Мгм. Да. Правильно. Будет, что альфа минус бета при голоморфном пересечении А. Оно так и есть или нет? Где?
Нет, оно так и есть.
Что? Оно так и есть.
Но нам нужно посмотреть, как оно.
Голоморфное или оно на пересечении?
Ну вот альфа минус бета мы знаем, как выглядит, да? А,
Ну, конечно, гомоморфное на пересечении. Потому что пересечение.
Казалось бы, да.
ага.
Я пока не вижу, как окончить это рассуждение.
Ну да, ладно.
Всё.
Да, использовали аппаратуру вот эту?
Что?
Для записи все использовали приборы, да? Для записи, когда...
Ну, вроде бы да.
А, хорошо, то есть вот вы сильно эту штуку, да? То есть вы
Да, да.